YouTube. In this video, we're going to revisit some pretty basic properties of logs, but we're going to extend it really to common logarithms and then kind of lead into the natural logarithm. So let's take a look at these four basic properties we see here often. But basically, we'll start with this first one. Log base b of 1 is always equal to 0. And of course, if we were to re-represent this here, if I can write on top of this here, we re-represent this in an exponential form, we say, of course it does, because b to the 0 does indeed equal 1. And of course, log base b of b is always equal to 1 just because b to the first power always equals b. And so we could say b to the first always equals itself. These last two properties here we say are inverse properties of logarithms and exponentials. So basically, if you take a logarithmic thing of an exponential thing and they both have the same bases here, you see it b, then they cancel each other out and we get left with basically just the exponent here in this particular expression. And then down here, if we had an exponential thing like b to the power of something, but that thing that we're taking to the power of is a logarithm that has the same base, then those cancel out. We get left with the argument on our log here. Those just cancel out. We get left with the x. So basically, we can extend these properties here to be for any base. Basically, that means that it works for common logs as well, which are specifically base 10. So all of these that you see over here, it's just kind of good to recognize these, like log of 1 is always 0. You know, that's what we're writing over here for any base. Log of 1 is always 0. But you know, log base 10, people tend to get a little confused when they don't see the base down here. So basically, log of 1 is 0. Log of 10 is always 1 because, of course, this is log base 10 of 10. Log base b of b is always 1. And then these down here, of course, this is log base 10 of 10 to the power of something. So the log and the exponential cancel out. And then, of course, this is also 10 to the power of log base 10. You can see that these have the same bases here, and so they cancel out and leave behind the x. And so we just don't write the little subscript 10 there. So to talk about another very, very specific log, let's take a look at our natural logarithm, okay? So we've looked at common logarithms and properties of all logs. Natural logarithms are a function that is a logarithmic function, but with a base of e. So the base e, recall that e is this number that is approximately equal to 2.718, and we refer to this right here as the natural base. That's what e is. And so when we make e the base of our logarithm, we see things that look like this. We say log base e of x, and that is the same thing as ln of x. And essentially what this stands for is the natural logarithm of x. And that's how you would read this. This is the natural logarithm of x, or you could write log base e of x. I know that I've had students that write this log base e of x just to be explicit here that they like the e. You know, you got to get used to, though, the ln, because everybody's going to be writing as ln of x. So ln of x is shorthand notation for log base e of x, and we see functions like this often. So let's take a look at a couple down here. We say y equals ln of 4 minus x. I'm going to write this here. Y equals ln of 4 minus x. And so if I were to rewrite this a different way, and I don't encourage this, but I want you to see this, this is the same as y equals log base e of 4 minus x right here. This is really the same function that we're talking about right here. But if we were to find the domain of this, recall that for any logarithmic function, at least a parent function that hasn't been shifted, they have a vertical asymptote here and go to the point 1, 0, and then their base comma 1, and they grow very, very slowly. But essentially, we can only take the logarithm of positive numbers, okay? So whatever's in here has to be positive. We're going to write a little note here. Must be positive. And so what we're going to do is we're going to take what's in here, and we are going to set it greater to 0. I'm going to do my work over here. So we say 4 minus x is greater than 0, and we're going to solve for x. So we're going to solve for x. And so solving for x, I would subtract 4 from both sides here, and of course we would get negative x is greater than negative 4. And when we divide everything here by a negative 1, remember that multiplying or dividing both sides of an inequality by a negative results in switching this middle sign here. So we would get this, we would get x is less than a positive 4, and we would say this is the domain of our function right here, that right there. And so we could say that also, we could say x is less than positive 4. That's negative infinity up to 4. Those are all numbers less than a positive 4. So here's our domain. Now, finding the domain of this one here, we would just say that this inner portion here, the part that we're taking the log of, has to be positive. So we say x squared has to be positive. Now, the interesting thing about this is that it is a polynomial inequality, which means, yes, we have to solve for our critical values. Our critical values, by the way, would be what we get when we solve this equation here. And taking the square root of both sides, I know this seems rather lame, but we get plus or minus 0. Or in other words, we get 0 twice. And so we have one critical value. If we were to represent this on a number line, it's kind of nice. Our critical value is right there. And so I'm going to test two values right here. I'm going to say -1 and +1. I'm going to test those here, 1 and -1. And so when we plug these in the function, if I plug in 1, I get essentially this statement here. I get 1 squared is greater than 0, which is totally true. You'll notice that -1 would also satisfy this initial inequality. So we'd say that it's all of these values right here on either side of 0. Now I wouldn't say 0, and the reason why I wouldn't say 0 is because if we square 0, 0 is not greater than or equal to 0. So we'd say it's all real x values except for x itself. So we say the domain of this function right here, I'm going to write it up over here, the domain would be domain -infinity to 0, but don't include 0, and that's in union with 0 to infinity. So kind of interpreting natural logarithms is just basically logs base e with a base of e. Then we're going to extend our initial properties here, which are true for all bases b here, to just natural logarithms as well. So just recall that, if you take the log of 1, no matter what the base is, you're going to get 0. And if you take log base b of b, in this case we say this is really log base e of e, so they cancel out here, and so we get 1. And then also this, we say a logarithmic thing of an exponential thing. You'll notice though that the base of this exponential thing here is e, so the log and the base have the same bases here. They cancel out, then you get left with this little exponent here, x. Also, if you had an exponential thing, look at the base of this exponential thing, e to the power of. Well, it's e to the power of a logarithmic thing, and that logarithmic thing has a base of e. So since their bases are the same and their inverses of one another, they cancel out, and you just get left with the x right there. So let's go ahead and take a look at a situation that involves a natural log here. We just have this model, and I just want to kind of point this out. We're going to read the problem here, but you could see how maybe like a logarithmic function would come up and through these data points right here. We're just using a portion of this graph to model what this data is doing. We say it's a good fit. So when we read through this, it says when the outside air temperature is anywhere between 72 degrees and 96 degrees in Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. We could see that here, it climbs by 43 degrees. It says the bar graph in figure 4.16 shows the temperature increase throughout the hour, and the function, and we see this here, f of x, or y, equals 13.4 ln, or natural log of x, you just say ln of x, minus 11.6, models the temperature increase f of x in degrees Fahrenheit after x minutes. So one thing I want to mention here is this, and this is always good to write down. This is f of x, and we say temperature increase. So I'm going to say f of x, or our y values, are indicating temperature increase over time. And I say time here, that's because our x value here, we said, is time. And we're measuring this, and I'm going to write in minutes. And I should have written units over here. We're going to say in degrees Fahrenheit. Degrees Fahrenheit. So that's kind of important because it just means that every point on our graph gives us a time, and a temp increase. Temp increase. That's what it is. Not temperature, but temperature increase. So it says, use the function to find the temperature increase to the nearest degree, whole degree, after 50 minutes. And so how well does this function model the actual increase shown in this figure? So when we say 50 minutes, well, I want to point this out here. We're saying we're given a time. In terms of both parts of my function here, in terms of x and y, I've been given an x. So if x equals 50, we're certainly just asking this, like let's plug 50 into our function, and we'll find out, what would this f of x value have to be here. So we say f of 50, function value of 50, we get 13.4 ln of 50 minus 11.6. And so let's check this out. On a calculator, you're going to see that you do have an ln key, of course, right probably next to your common logarithm button. But we're just going to type in what we see here. So let's go and turn on, we get 13.4, and then we'll just hit ln. You see that it gives you kind of a beginning parenthesis. We're going to say just of the 50, and then end that off there. And then we say minus 11.6 is, that was on the outside of the logarithm there. And so we hit enter, and we say 40.82. So I'll fill this in here, 40.82. Now, looking at the date over here, we say at 50 minutes, it's actually at 41 degrees. And so the interesting thing about this was to the nearest degree is what we desired here. So I would say that it's safe to say that this is 41-ish degrees, 41-ish degrees Fahrenheit. And so this model is pretty close. As a matter of fact, the model only underestimated by about 18 hundredths of a degree. And so again, if we wanted to look at 30 minutes, this is the same idea. We'll just plug in 30 now. And so we say, what is f of 30? And so going back, the nice thing about this calculator is, of course, we can hit second and then enter. It's going to pull up the last thing I typed in, and I'm going to just go back to the 5, change it to a 3. We can see it's about 33.98-ish. So I'm going to say approximately 33.98-ish, and of course that's to the nearest degree, approximately 34 degrees Fahrenheit. And so at 30 minutes we could see that this model is really, really accurate at predicting where the data is going to be in the data set. Cheers.